Hello everyone, my name is Desmond Aubrey. I'm from a company called Rarefied Technologies, or RareTech SEA for short. And the topic today that I'm going to talk about is copper brazing, copper-based brazing really, because we've got different types. And here we're talking about brazing essentially foils or microfoils. And the first project that I'm going to talk about will be a project called CuproBraze, and then the second project will be called XBraze, and I'll go through the details of what these are about. I think it might be quite novel for many people to come across some of this, so we'll talk it through step by step. So CuproBraze, what is it? The CuproBraze project was developed actually in order to braze copper brass automotive heat transfer devices. You were trying to, in the old days, copper brass radiators were soldered together, or as the Americans would say, soldered. So you would use a solder to join the fin to the tube, but the joints were not that strong. It was very easy to break them, and the radiators themselves needed lots of lateral or side support to give them the strength that they required. And so a team in Sweden actually decided to start investigating a special type of brazing process to replace the solder process. And this particular company was called Outokumpu Copper Strip, or AB if you want to call it at the end. And they were based in Västerås in Sweden, and they had an ancient history. They went back something like 400 years as Svenska Metallverk, and they'd been in the industry for a long time, and they used to launch actually from a port that was an old Viking launching port that they used to transport copper all the way down to Stockholm. You could get there by river and canal. So they started this particular process. And so the problem is, though, when you braze, we braze at very high temperatures. We're brazing over 600 degrees Celsius. And at those kind of temperatures, the copper fin tends to anneal. Annealing means it gets soft, and you end up with a very, very weak product. And that's a problem. And it also happens to a certain degree to the brass fittings as well. So what had to be developed was a special anneal-resistant copper fin, okay, that in fact would not soften during the brazing process, and also to develop anneal-resistant brass components, things like headers, side rails, and fittings. And then you needed to kind of join this all together. All right, it had to be now brazed. You had to have a special brazing alloy that would actually work on these products. So what Outokumpu did is they developed an anneal-resistant copper fin. They put in a certain ingredient, which what would then happen is as you move through the brazing process, this ingredient would move around inside the copper, and then it would actually strengthen and stiffen the copper. In fact, it was so stiff after brazing you could actually make it ping. It would sound like a little bell. It was actually quite amazing. And then the tubes, they also put a different type of ingredient to actually control grain growth, because what happens is as you raise temperature, the grains start to grow, and then you end up with basically a very weak structure. So they had to control that in the brass materials as well. And another special complication was that brass actually has zinc in it, and zinc causes all kinds of complications when it comes to brazing, because you're forming a zinc oxide, especially at those elevated temperatures. So we had to be quite careful. Anyway, I'll get into more detail as we go through. And then they developed a special braze alloy, a eutectic alloy that could actually melt at those temperatures of brazing and actually then form this braze joint. And so what was the original idea? So this was actually for radiators. This company was mainly involved in supplying a radiator strip around the world. They supplied over 70% of the world market at one stage. They had fantastic operations down in Finspång, which was the other center, their manufacturing operation. They had a really, really good production line down there. That line has since been moved to Zutphen in Holland by people that bought out Outokumpu later on. So they were focusing on cars, trucks, off-highway, earth moving. Things like charge air coolers, for trucks, big, heavy things, perfect for this kind of application. And heaters for cars, because a lot of heaters in those days were still actually copper brass. So now, the reason that they wanted to do this project was because of the aluminization. In other words, all vehicles were becoming aluminium based. And there are restrictions as to what aluminium can actually do. And you'll see it in the marketplace where people try to use aluminium on certain components. It's very soft, it's such thin foils that they get stone damage, whatever. And especially in Russia, you would go through an aluminium radiator in less than a year. There'd be a big hole in the middle of it, depending on where you were. Whereas copper and brass are much, much more durable. So just to talk you through a few pictures, this is actually a very nice example that was made up of a CuproBraze radiator, in this case using brass tanks. Looks really, really impressive. The trick is, we did a few tricks, and I'll talk through later about my part in the program. And they ended up with a very, very bright product. This is, to get a bright product, you've really got to know what you're doing. If you're not careful, they come across cloudy and doesn't look nice at all. So, and it also, that's a sign that there's some level of either carbonization or oxidation. So this is what was coming out of the brazing furnace. And this is an example of a brazed core. What you have here is the anneal-resistant copper fin, and you have the brass tube. The brass tube originally starts off as a yellowy color like you'd see here or here. But what happens is the braze alloy actually wraps all the way around the tube. And it eventually, this is the color of the final braze alloy. It's a copper, nickel, tin, phosphorus system. And they use the tin to drop the brazing temperature, and the phosphorus acts as a bit of a scavenger. So this essentially, there's no flux involved for this part of the process at all, actually. So it was quite a unique process. And this is an example now of something similar to this, a radiator, but it's got the normal plastic side tanks, the crimped on side tanks that you'd see in the aluminium industry. And this is actually a joint profile. What you'll see here is the copper fin. You'll see the copper nickel tin phos brazing alloy, and then you'll see the brass tube surface. There's a few tricks that we can talk about here. What's interesting is to watch what's happening over here. There's a little bit of alloying where in fact the part of the copper fin starts to get diluted by the braze alloy, and you're forming kind of a bronzish type component. And then on the tube itself, it also gets a slight migration into the tube surface. So you get a very, very strong, solid bond, It's not easy. You'll tear the fin off before you can actually tear the layer. And there's quite a bit of art to getting all of this right. So I'll talk you through a little bit of how I got involved in this process. It was originally developed by two technology teams under the International Copper Association, or an RCA initiative. They're based out of New York. More as let's say a copper representative body, international representative body. And the two teams were Outokumpu Copper Strip AB from Westeros, who did the anneal-resistant copper, the anneal-resistant brass components, and the braze alloy. They invented all this, and they got patents on all of that at that stage. It was really quite a trick, actually. And then there was a team of developers in the US under the RCA. These were people that, there was a few good names in there, gentlemen that had retired from the industry, but really good people as well. But truth be told, they had come to a point where they'd been on the road for about 8.5 years on the development pathway, and they weren't getting anywhere, right? They basically, my background is I'd come from a project that we'd done in South Africa on aluminium, which I helped to commercialize, called the CD composite deposition process. And then I was looking now to spread our wings for this group into copper brass. And so it ended up with a meeting with Outokumpu and the guys from the US and so on. And we met in the UK, in Rugby actually, at our technology center at the time. And what then happened is I kind of did everything I needed to do on the aluminium side, and I was getting a bit bored, and the group was looking at restructuring. They had a big claim against them in the UK for asbestos, and so I was looking for a new challenge. And what happened is Outokumpu and I got talking about this and how we could actually collaborate. And eventually I offered my services there as a consulting engineer, and they took me on. And so I went over there. Initially it was going to be for 3 months, And the idea was, let's see if we can make this process work. Because, truth be told, the parent company, Outokumpu parent company in Finland, wanted to cancel the whole project. And so I managed to help them understand that, one, we could get the costing right and be very effective in those days on the copper price of the time versus aluminium, and actually save money if we were careful. And then part of that 3 months, I ended up going in and sorting out a brazing furnace. They had built a brazing furnace, but it didn't work. I actually went in and had a look at this thing, and I said, no, it's not going to work. And we brought out one of the metallurgists, and we realized it was actually a lot of zinc coming off, and there was a lot of oxygen control problems and everything. So it was a furnace that looked something like this, actually, very similar. So then we had contact with the furnace builders, and said, I want a few tricks put in, which I specified to get the control of the atmosphere right. And then also, it's very important, so that if you get any binder burn-offs and so on, we control it as much as we can. Otherwise, you end up with a very dirty core, like I'm talking about over here. So we don't want it dirty, we want it shiny like that. So there's a lot of tricks in oxygen level, parts per million control in the atmosphere. And so, long story short, I was engaged by Outokumpu as an executive consulting engineer based on my experience in South Africa. And then basically I built up an engineering team to guide the project from laboratory scale to commercialization. When I got there, frankly, there was a lot of doubt even within their company as to whether this CuproBraze would succeed. And I had to then kind of use my engineering team building skills to kind of get everybody on board. They were all fighting in different directions. Only a few at the start. I think there were about three of us really on the technology, then me fourth on the technology side. So I managed to get everybody together, got the guys from Germany, everybody who was, the subcontractors, and got everybody moving. And then eventually what I did is I helped to bring both teams together under Outokumpu's technical direction, with the RCA managing the marketing more than anything else of CuproBraze technology. This made sense because they were pulling in different directions. And when I got on board, frankly, they didn't even have a tube to header joint. They had pretty good tube to fin. That was nice. This was good. But when you start to get into these areas here, it's very, very tricky. And you've only got one shot, when you pass this thing through a brazing furnace. It's got to be perfect. And there was a problem with the tube to header joints and these side rail joints. These are not too bad, but the tube to header was a real issue. And then doing the tanks was an issue as well. So what I did is I then rousted various people that have been involved in the braze alloy side, the binders, if we want to call it, and then helped to engineer binders and get them to. We actually organized trials in Pittsburgh with a furnace similar to this, and to get them to come and test out different directions until we could actually get a good tube to header joint. What happens with brass? Because of the zinc in the brass, it tends to what we call de-wet. In other words, the braze alloy will start to wet, go in the joint, and then it'll jump out. And then you will basically have huge problems on the tube to header. They don't seal. So we had to develop techniques on how we would actually get the tube to headers to seal. There was quite an art form to that. It's not as simple as most people think. It's actually not as simple as aluminium. Aluminium, you just use flux and you spray it everywhere, and you have eutectic layers and so on the components. And it's pretty easy. But when you get to this, you've got to know what you're doing. So I could bring a lot of my expertise that I knew from CD technology and apply it here, at least try it until we could get to some success. And so the first 3 months were quite amazing, and actually the end of the third month we actually had successful brazing trials in front of an international team. And my boss at Outokumpu, he was a real character. He was virtually crying at the end of the line. He says, I've been waiting for this for 8.5 years. Look. He was crying. But I'm on the other side. I'm feeding the cores into the into the furnace, and I'm seeing binder smoke coming out, and I'm not happy. But other people didn't see it. But I saw, and of course we then had a lot of work to do, because the initial binders that they used actually to get to actually hold the particles, because what happens, the copper, nickel, tin and phosphorus is a particle, and it's very small, and it has a very high chance of oxidizing, and then it's pretty useless. So you've actually got to protect it with a binder. and again what binders. And the binders they were using at those stages, there was a spray binder, which actually was not bad. It was a water-based binder, and then there was others that were like wax-based. And of course, wax, makes a lot of fume. It depends on how you crack it. And I remember trying to talk to the designers out of Germany, and they're a little bit stubborn about what they could or couldn't do. Everybody's trying to protect their know-how and so on. But eventually, we ended up with a good product and good technology. And it's actually, we built a solid technology that was used extensively internationally, actually by a number of manufacturers. And that took me around through like over 32 countries at the time, supporting our local marketing teams. And during that time, I conducted over 150 technology seminars, actually more probably, in numerous languages. What I'd have to do at the time, I would go in and I'd have a cheat sheet of the slides in English, and then the slides would be in Chinese or something, and then they would talk in China about it, So I had a Chinese colleague that would work anywhere else, wherever I was, if I was in Thailand, I would go talk in Thai and so on. But it was really interesting. It took me all over the world. At one stage of my time, 80% of my time was in an aeroplane, flying around the world, getting this technology set up. But basically, we did okay, actually. So, just to show you one of the last projects I was involved in, certainly, there's a large furnace. This was a convection brazing furnace that was eventually, if I remember rightly, this was installed in Russia by a company called Warwick. It was built in Poland. I went to the commissioning trials. So there were a few issues, but it was a comprehensive, nice furnace, gas-fired. And then there's this continuous radiation furnace, which is really similar to what I ended up using in Pittsburgh. And I put a few modifications in it. I got them to add which made it really tight, And this was made by Abbott. Very nice, simple furnace, and actually I thought very well priced too. But this was a radiation furnace, but it was using gas around to give a radiation effect to do the brazing. But actually nice. You get a nice warm muffle. The muffle's the part that the belt goes. There's a belt here, and you put the core on there, and off it goes down through the furnace. And then I was involved in helping to develop a two-bay batch furnace, also with Warwick. I sat down and we figured out the idea. It's a low-cost furnace where you could actually put a component on, feed it into a chamber, draw down, bring down so that the oxygen was kind of out of the system, nitrogen control, put it into the braze zone for a period, boom, bring it back, index it back, and then let it cool. So this was a combined inlet chamber and a cooler. So I helped to get them to think it through, all in the good of this project. And then I see the Swedes went ahead and with their own kind of furnace, which eventually they got it to work. In the beginning it was kind of in a dog's leg shape, and they eventually got it to go. They'd put the part on and they'd index it through. So what would happen is you have a part here where you now control the atmosphere. Any burned up binder, you've got to be careful though. So you take the binder off, you move it down into the brazing zone, and you heat it, and then I think on this one you're going to bring it back again as well. So that was a different kind of design, but it worked, and it's used in, I think it's still sitting in the brazing center in Sweden. So that was my role really. And then there was another furnace. I remember this one. This was for a company called RHVAC, and the guy, he was a German guy, a German-American designer, and he picked my brains on, he wanted to build a batch type furnace. You'll see this is the end cap of it. And he had an idea of actually putting in elements and so on. And I advised him on it, and I said, I think you'll be okay. It looks fine. It's a different way of doing it, because RHVAC, it was for a company called RHVAC. They had very, very, very heavy cores. And it's very difficult, also with these kind of side rails and to support it and everything else. They wanted, and to get better tube to header joint integrity, they would prefer it to stand it this way. So you actually get your braze alloy in here and braze alloy in there nicely. And this is the kind of furnace that he put together. And then you would close it in. The way it worked is you'd actually close a cap, bubble cap, close it up, pull it down tight, and then you would actually pull a partial vacuum. So you start to evacuate any air that's in there. It's before you apply heater, you evacuate, and then you start to backfill with nitrogen. Flush it out again a few times until you've got a pure nitrogen atmosphere. And then they would then start to apply the heat. You don't want to apply heat under vacuum, because then you can start to pull the zinc. It volatilizes out of the brass, and then you get a problem. Okay, this is the problem with brasses. And so this thing actually worked well. And he also worked, I had a few ideas at that stage, very contrary to the rest of the team, but where you actually used a certain dash of hydrogen in the process. And hydrogen is amazing. It helps you to get very good joint filling capacity. And so he put a little bit of hydrogen into this as well. But you can be careful. There's a limit. I think it's about 8%. Got to be careful with hydrogen. Really know what you're doing. And he was quite good at that. He designed this furnace. There's a fan at the end to circulate, and he would circulate it back through, if I remember rightly, it blew, and then across the core, and then out through the back here, through the shell. So it kept the shell cool. And then what he would do is he would open it up and then get cooling. I think he had a cooling jacket or something through here. It was quite a sophisticated furnace. It worked quite well. So it's a very different design, different ideas to these kind of furnaces. This is more classical, where you've got your radiation, you've got your convection. Sometimes you get a mixed. You get a radiation, then convection. The radiation tends to give you a very nice, if you get it right, if you've got your gas all the way around, it gives you a very nice even braze. Convection tends to pockmark it because you're actually blowing hot gas down onto the actual component, a bit like a microwave oven. So there are some limitations also with convection. This was a convection system. This was, I think, radiation. No top fans in this at all. And then what actually happened is Shaz and Shadrinsk, in the city of Shadrinsk, this company was called Shaz. They wanted to do this in Russia. And this is just showing them actually producing. You'll see here, this is the fin machine that makes the fins, and then feeding down onto a feeder table. And then they feed the fins down, and there'll be somebody at the end picking and putting it together to actually assemble the bundles. This was a little bit, I thought, a little bit too it wasn't such an automated line as I was used to in South Africa, but it did the job. It was kind of in between semi-automated, if you want to call it that. But they seemed to do quite well, and they were making products for Kamaz and for these big trucks off highway. And this is a charge egg cooler. If I remember rightly, I think this is one of these, and where they actually did the braze core, and then it would come out, and then they would actually braze up by hand the end tanks, because there's a total difference in mass between an end tank, a big pressurized end tank like this, and the core, and then it's very hard to get it right in the furnace. So what's better is to actually do the core and then to do the end tank separately. And you see the same with aluminium too. They have to, because there's a problem even in Knockalock. I've seen lots of rejects at companies, even like Vallejo, big names, and that where they've had to, braze it up in that to get it closed. Even sometimes braze tube to headers. So it's tricky. And this is my friend Lars Sham. I don't know if he's still around, Lars, but he was actually in the workshops in Westeros originally, and he kind of went around the world with us many times to work with customers, and he got very good eventually. This is one of his jobs there. Super guy. What a nice man. A thorough gentleman. And there was another guy, Janne as well. I think Janne, last time I saw him, he was running the a center, what do they call it in those days? Let me just see what we called it back there, brazing center, and they'd moved it from Westeros down to Finspång. So I had a role right through up until Shaz. This was my last project with him. I felt that I had done enough, and it was starting to get too political for me. I'm one of these idea generator guys who gets stuff going. I don't like all the politics, okay? But I was literally, bottom line, if I hadn't have got involved in this project, it wouldn't have succeeded, because they just didn't have the foresight that we could get on with it, we get it done. And we got it done. We really did get it done, despite a lot of hurdles at the end of the day. But I think what also made things difficult is the price of copper suddenly rocketed. The copper guys that said, copper won't rise, it'll be fine. And we went with that. But it suddenly rose, and it priced themselves out of the market, which is a bit of a pity. Now, this product, CuproBraze, was restricted to automotive applications and heavy-duty related stuff, and even things like earth-moving equipment and so on. And they never went into the HVAC or the commercial game. And there was a reason for that, because I won't go into too much, but there were two different divisions in this particular company, and I won't tell you its name. And you can think about who it is. And the one guy focused on brazing or automotive division. The other guy focused on commercial, and the two bosses hated each other. So we couldn't get technology to transfer between us. And I felt that there was a huge prospect in the commercial and HVAC side, and which is now slightly different. And they just couldn't get it off, and eventually that was the end of it. So CuproBraze, I think it's still going in parts of the world, and there's a lot of different products that you can do with it, but it's really a very, very nice technology, but you do have to know what you do. So that was a bit about the CuproBraze side, okay, and my role in that. But it was fun. I enjoyed it. And then just to talk a little bit more about another process, I call it XBraze. Now, what I had said to you before is that CuproBraze focused on brass tubes and copper fins, anneal-resistant copper fins. And I felt that that was a shortfall, a deficiency. So what actually happened? I was given the name of a South African company who was making these very special tubes. They would actually work them from something like this, down into this flat form. And they made tubes like this. They're really nice, and tubes like that. You can see the size of it. Tiny little guy. I think this was 16 millimeters wide. Tiny. And I was fascinated because I thought this is really going to take the game into HVAC. All right. So what happened is the guy who was running the company, managing it, a really nice chap, he managed it for the owner for quite some time. And so we got going and we said, okay, let's put a project together. Let's see if we can get your tube commercialized. Again, I can open up the international market. I'd gone back to South Africa for about 4 years at that stage, and I was trying to promote a lot of this in South Africa to boost their economy. So what was the idea? The problem here is you've got a copper tube, and this particular copper tube is not anneal resistant. Excuse me. It's not anneal resistant. So you've got to understand very carefully what you're going to do when it comes to brazing, because it will soften. But the question is how much, and how much is good enough. So this is where I had a bit of a thing to work through. So I developed a process to braze anneal-resistant copper fins, the fins that I showed you from CuproBraze, the same supplier, to high-strength copper tubes. Now these are very strong, but they are not anneal-resistant. I will just say that. And I've always had the vision of working with copper tube manufacturers to help them to understand how to make anneal-resistant copper tubes. So that's something I can certainly help the industry with. And the idea was to braze high-pressure HVAC, heat transfer devices. Now, what am I talking about here? Things like condensers, evaporators. At the moment, the way it's always been in the past is you would have a copper tube, excuse me, and an aluminium fin. All right, they squeeze these fins over the thing, but they weren't brazed. And when you braze something together, you get very, very good heat transfer. And so the idea is to actually make a very compact, strong system that can go into the HVAC industry for their evaporators and condensers. And this has always been my vision. And then to also look at high pressure commercial heat transfer devices. So what you're effectively doing is you're taking tubes like this. This is very strong. And tubes like this that are not going to blow up under pressure. Because what happens if you're not careful, when you've got a fin tube construction, I'll just talk you down the presentation a little bit. When you've got a fin tube construction like this, if the tube is not strong enough, it starts to swell. It swells up and eventually it crushes the fins, because the fins obviously have some structural rigidity and strength here. But once the tube starts to belly, you basically crush the fins. Okay, it's one of the tests that we do in radiators. So the idea is to have a very, very strong tube. I mean, this was a really, really nice tube. The problem is they never went to full commercialization because they had some problems in their production line to be able to get these centers all very nice and sweet. And I think personally the people that were doing it struggled a bit with it. And it was a pity, because this was a tremendous technology. So anyway, the long story short, the guy that was managing at the time, he and I put together a project, and we then said, right, let's try and braze these things. And this is the result. We ended up, look at these kind of joints. What I did is I got the fins sent over. We ordered fins, a whole lot of fins, and very kindly it was supplied by Outokumpu at the time. They were kind enough to supply them. And then we had the tubes supplied by this company I was helping. And then I had braze alloy, which I've kept secret on what it is, supplied by yet another company. And we then put together a trial of 50 little cores. And it was very interesting. Right? We didn't even have a decent furnace. We had to use a lab scale furnace, and we had to do some tricks to control the atmosphere and basically a hot box and so on. And it was a lot of fun, and we had success. we really got it right, and backfill with nitrogen and so on. So this is an example. Here you're seeing the tube. Now it's not silver like copper brass. Why? Because it's not brass. And the wetting ability of these alloys onto copper, so copper to copper, you have a copper fin to a copper tube. It's different from copper to brass. The flowing characteristics are very different. So like I always say, copper sucks, and it does. And you have to understand how to control that. So your brazing profiles are really, you have to be quite slick with what you do. And so this is the kind of product we got out. Here's a sample, looking under the microscopes. I was checking the joints and picking all this kind of stuff up. And the joints were stunning. I mean, if you look at these joints, I mean, this is like, hey, I was over the moon. What you're seeing over here, these are micro louvers that you have in these kind of tubes. And here's an example of what you might think a furnace profile would look like. But yes and no. Okay, there's some tricks to all of this. But this just to give you an example of the kind of temperatures we were working at and so on. But you have to control this. You've got to know what you're doing. The important part is your control over the melting point temperature of your alloys. And if you control for too long, what actually happens, firstly, the copper itself softens if you haven't made it anneal resistant. And then you also start to get alloying of the fin here. This is where you've got to be careful. And that then it will start to affect in other words, once you take copper and you alloy too far, it becomes bronze, and the heat transfer coefficient of bronze is quite bad. Not the same as copper. Copper might be 330 watts per meter Kelvin. Bronze might be 18. Okay, so that is our control problem with all of these kind of brazers. So anyway, I developed this process on how to get this done, and I call it XBraze, and it really is very nice. And then just to show you, there are a few other tries that people did around the world. This was a project done in the US at a university, and they managed to use a different way to make a multi-port, but the problem is commercializing it. I don't think it ever got to success because the copper itself, copper tube, is notoriously abrasive, and he had a very different type of operation where he used kind of an extrusion process, but it is tricky. But there are ways to get that better, and this is where I was hoping they would go a bit further, but their licensing, they got a little bit greedy, so I backed off out of that. I was looking at a way to commercialize it, and then my RP attorney said, be careful, because if they mess you up on the front end, your back end work is a waste of time, so don't do all that. So I backed off. But basically this is another kind of idea. Now I'm hoping that the industry will have advanced a little bit since then, actually, from where we were. All right, so just to recap, you've got this high strength copper tube. You blend it with an anneal resistant fin, and then you braze using what I call the XBraze process, and it's my know-how. I'm the only guy in the world that's done that to the best of my knowledge, and with success. So what I'm really looking for is people out there that want to start to get into this copper brazing. I think we can say, safely, that if you go back to CuproBraze, CuproBraze kind of got it to a certain point, and that we need to go beyond that, because the industry has changed. copper brass in the automotive industry, eventually in cars it became too expensive. Trucks, they still, I think, use it, but most of it's aluminium, and aluminium doesn't last very long. Off-highway, earth-moving, I've actually seen problems with aluminium and earth-moving. They just crack and fatigue, where copper brass is much stronger. So this process has kind of matured quite nicely, and I think it's fitted in with what it needed to do. But the technology really shouldn't have stopped there. In my view, that was a real shame. And I remember approaching various leading bodies about this, but they were too political, and we couldn't really kick a project like this off. Now, what I would like to do is this is why I'm making this movie, is to actually put together a technology team to promote moving into copper for the HVAC business, because I think this is a tremendous business. I've done presentations, and I'll probably put that together also as a show, of the kind of potential volumes out there. It is astounding, and it actually would work very nicely, this process, in the HVAC industry. I actually was hoping to put this into my micro heat pumps that I make, because it's really compact and nice, and you can make a very small unit compared to the traditional standard type of system. And also you can play with the fins. It doesn't have to be this type of high performance fin. You can put there's different types of fins that you can put in there, structures, offset strips, all types of things that are very robust and very strong, and they may not blind with water and so on. So there's different technologies you can apply, but the principle is brazing them, all right, rather than at the moment what they do is they just slide these fins over. It's a kind of a loose structure, and then they've got the ends on it. They just lace everything up with pipes and everything, but it's really not that robust, to be actually quite honest with you. Whereas this is a very robust system. I remember on the CuproBraze side, a gentleman from Russia, when he first came to visit, he took a core that looked similar to this, and he said, I'll just bend it, because aluminium, if you take aluminium, I'll show you, I'll go back to the gallery for CuproBraze. If you take, as an example, if you cut here, all right, and you cut it off there, take the headers off completely, just put a bandsaw through there. If you do that to an aluminium core, and then you put this end on the ground and you start to roll, I call it the Swiss roll test. The aluminium radiator will roll into a little ball, into a little cylinder. You try that on a CuproBraze core, you can't even bend it, man. It's just so strong. It's amazingly strong. And it's the same also with this XBraze process, of course, even more so when you've got these very robust tubes. It just doesn't go anywhere. Very, very strong. And if you, let's say you take an instrument and you run it over the fins, they actually ping, ding, 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 ding. So it's very, very strong. They've become stronger after brazing than they are before brazing, which is quite astounding, all right. So that's the beauty of this technology. But to my mind, it was just such a shame that it never went any further. And the South African operation, their problem was they really were not geared up at that stage. And the owner, I don't think, really fully understood how to gear up. They were talking about different types of machines, but they didn't have the technical know-how. And then eventually the owner, I think he sold up the business later. And then the new owners that took over just really didn't know very much at all. But it's a very, very good technology. I thought I'd introduce it and let people know about it. So why am I doing the video? I'm doing it so that people, one, can be aware of the new possibilities that are out there. And I'm very much looking forward to companies or individuals wanting to put together something like this, because, you know, I would imagine in China there's many manufacturers who would have the capability to work this up to the next generation, okay, and even slim it even further than this, all right, and also to make anneal-resistant materials. And I can advise on that and how to actually get it right, and advise as to what we learnt from CuproBraze on how to apply some of that into XBraze. The anneal-resistant fin, no big deal, but at the brazing technology, that's my know-how. It's a secret in-house. I've never divulged what it is, but it worked well. And so I'd like to partner with various people and think about projects that we can actually launch. I live in Southeast Asia, and I'd be very happy to partner with people to launch this technology and to help them get them on the go. I think it'll make a huge breakthrough for the HVAC industry, because I know I used to be on the HVAC forums and talk to various people, and they were just saying when, you know, because people have been trying to bring in aluminium to the HVAC industry, and aluminium is really not suitable. For instance, people like to braze everything together. It's a very robust industry. People like to braze things and braze joints, and aluminium is troublesome. And also aluminium, I've seen people try to make multi-port tubes. You know, they make it from strip, and then they try and close it all up and under brazing. It's very dangerous. You're using very high pressures. You know, if you go into things like carbon dioxides and that, you've got pressures up, I think it's about 200 bar. You can't play the fool with it. It's got to be right. And so, and some of them really, you know, up in the 30, 40 bar range. And you can't do that with CuproBraze. CuproBraze will just blow up. So you need something very robust. And this is where I believe that XBraze is the way to go. So I've got that pretty licked, and I actually proved it nicely in South Africa. And so I'm really looking for people who would like to talk about it and see if we can put some projects together. The idea would be to get a nice little young super team together of engineers who've got, who want to make a new, forge into the future. And I'd be happy to work with you and advise you and consult and talk through my experiences and what I've learned and what to do and what not to do. Okay, but also to help even right up to production level on how to actually get components done and where the limitations are and how to help with that. All right. And when I talk about limitations, I'll go back to just lastly on CuproBraze. If you look at a braze joint picture, the problem you sit with in CuproBraze, of course, is you've got the copper fin. That's cool. You say you've got to watch what goes in here. Brass, not so bad because it de-wets a little bit because of the zinc, but we get by there. And you'll see the actual grains over here, not so big. The grains are big there. But now when you've got copper to copper, you get the same problem as you have to the fin. But if you've got a tube that's not anneal resistant, you've got another problem. And the problem is that the annealing curve is temperature time dependent. And you've got to be able to manage that and control it. Okay, so this is the important part when you're dealing with these processes. So ideally we need to be sitting and talking about, don't have to, but ideally it would be nice to have an anneal resistant tube, and that's actually quite easily done. And so I've got technology and know-how which can help a copper tube manufacturer to in fact make his tubes anneal resistant. It's not that complicated if you know what you're doing. So I'm looking for that. That's why I put this video together. I hope you've learned something, yeah. And if you haven't, if you have any questions, get hold of me at RareTech SEA. You can get me on my website. Here is my home, and there I cover a lot of different things. I also talk there about, for instance, even things like advanced brazing technologies, which might be of interest to people watching this, where I show some of the samples that came out of those trials and some of those pictures that which you've seen. This is a bigger blow up of these joints. Very nice and consistent. And I've done a lot of work in aluminium brazing technologies. Here you see the grain growth, very problematic. Aluminium is very tricky. And brazing furnaces, lots of experience. I've advised people on all kinds of things, control. I used to run the Pittsburgh furnace very, very tight, and it was a nice furnace. It was a 4-zone furnace. The Abbott furnace was very nice. And so I was the expert for quite a long time on the CuproBraze project. So, all right, so that's a bit about copper, CuproBraze, XBraze, and a bit about RareTech SEA. So we'd love to hear from you. And thanks so much for your time. I hope I didn't bore you. I hope the sound comes through okay. All right, bye-bye for now. Bye-bye.